Okay, um, I'm Jim Miller. I'm a professor at Central Washington University, and right now I'm a retired high school math and science teacher. And I've been asked by the Cornerstone people to do a video on work, and I'm going to do this in four parts. So here's part one. And if you're comfortable with this part, you can skip to the next part. But in part one, I'm going to talk about the physics behind work and some of the units that you need to be familiar with. So, of course, work is force times distance. Now, in the English system, force is like pounds. In the metric system, force is in newtons. There are other units, but for most of the work problems you're going to deal with, you'll be dealing with pounds or newtons. Now, when you get work problems, sometimes they talk about the pounds, the weight. Force is a weight if you're working against gravity, or newtons. But they often will give you the problem, well, they'll tell you the mass of something. And so you need to know how to convert between force and mass. And if we're just talking about lifting something, then the mass is pretty confusing in the English system. And I could go into it, but I'm just going to avoid it. But the mass in the metric system is kilograms or grams. If you're lifting objects, generally we're talking about kilograms. To get from a kilogram to a newton, if you're just lifting something at the surface of the earth, you're talking about multiplying the force, which is mass times acceleration. The mass would be kilograms. The acceleration, which has units of meters per second squared, and that is 9.8 in the metric system. Let's write it here. Acceleration. In the metric system, it's 9.8 meters per second squared. So if you were to let something free fall drop, it gains 9.8 meters per second in velocity every second. That's what the units are telling us here. In the English system, it's 32 feet per second it gains in speed every second. So if you want to know what the mass is, you would take pounds divided by 32 feet per second squared, and you would get a unit for mass. It's a messy one, but we'll just leave it like this. So what are the units for work? Well, if you're going to take the force, pounds or newtons, times a distance, typically the pounds will be, you might be dealing with feet. And so the units would be foot pounds. If you're in the metric system, the units would be perhaps Newton meters. Now, a Newton meter is also one Newton meter is 1 joule, named after James Joule, the Englishman that was studying energy. Now, to get the pounds or the newtons, often they give you something called density. And density gets confusing when you look at different kinds of problems. So if they were just talking about, say, lifting water or oil or something out of a tank, the density would be in, say, in the metric system, kilograms per meter cubed. But that would be a volume mass density. In the English system, since we don't really know the mass unit very well, you don't really see a volume mass density. Now, they might give you the volume weight density. So this density of a liquid or a solid or whatever, the weight changes as you go up, get further away from the surface of the earth, and so the weight will change, the mass doesn't. And so that's why we often we talk about density more in the mass there. Another one is grams per centimeter cubed. That's another common unit in the metric system. But if we're doing the English one, they often give you the weight density, which would be pounds per cubic foot, let's say, or pounds per cubic inch, or ounces per cubic inch. That would be a volume weight density. In the metric system, it would be Newton meters cubed. That would be a weight density versus a mass density. In this one, the value of this changes according to gravity, how far away you are from the Earth, or if you're on a different planet, or you're measuring it between different objects. To get this, the mass density into weight density, you need to multiply by 9.8 or divide by 9.8. Here you would divide by 32 to get the mass density, 32 feet per second squared. So those are volume densities. In calculus, you often do problems with linear density. Linear mass density, or linear weight density. Example of this might be a rod or a wire or something, and they'll say, since it's uniform in its thickness and in its diameter, it's a uniform cross-sectional area, then they can just say, okay, there's so much mass per meter. Or they could say the weight, it's so many pounds per foot, or newtons per meter. If they give you Newton mass density, you need to multiply by 9.8 to get weight density, because weight is a force, and that if you're doing work, you're working with a weight, a force. If you're lifting it or doing anything like that, trying to find out the work on lifting it. Okay. You could also have area density. Not as common, and it could be by mass or area by weight. And these are just typical physics things. More often, I've seen in calculus books, they talk a little bit about not area density, but maybe population density. And so if you have a center of population, if you kind of draw it around the city center, there's a higher population and it tapers off if you go in any direction. So you could have densities there. Not very often you'll run into weight or mass densities in area, but you could. And then it would be pounds. The weight density would be pounds per feet squared, square foot. And so then you'd have to multiply by square feet to get the weight. Or in newtons, it would be newtons per meter squared. If it's in the mass would be kilograms per meter squared. And to go from here to there, you'd have to multiply by 9.8. Okay? That's some of the physics of density and work. Now, let's see here. What do I want to say? Oh, let's just talk a little bit about how much work it is to, say, lift something. So if I were to just pick up a person, 150-pound person, that would be a force. I would then, and if I lifted them 3 feet, then I've done 450 foot-pounds of work. If I were to lift a person similarly in the metric system, 150 pounds is 60 kilograms-ish. And if I lifted them 3 feet, 1 meter. But see, this is not a force. This is a mass. And so then I would have to multiply by 9.8 meters per second squared to get Newton meters or joules. And so 10 times 60 is 600 times 1 is, it's about 600 Newton meters or 600 joules. And there's conversions for those into calories or whatever. But so 450 foot-pounds is about 600 joules. Yeah, approximately. I'm just doing really rough estimates, but there. So lifting a person, lifting a weight of 150 pounds or about 600 newtons, about a meter high, is that. So there's an idea of just what work is about. Okay. And I should also say work is to lift something, you have to use energy, and the units for energy are also joules or newton meters or foot pounds. And if you lift something, that you're putting energy into the system, and that energy becomes stored energy or potential energy. And then if you let it fall back down, that would be release that energy, and that would become kinetic energy, the energy of motion if you're letting it fall. So just before it hits the ground, or it would produce that same energy that you put into it. If you have a totally efficient system, you're not wasting energy lifting it. Okay? That's the physics part of work.